I'm Coach Pete of Math Coach Me. I offer math coaching and tutoring services, and I also offer free lessons and resources at my mathcoach.me site. This is the sixth lesson in my trigonometry series. We're going to take a look at graphing the cosine function and its reciprocal secant function. Unique to my approach is the use of Desmos calculators like the one we're seeing here. Desmos offers an exceptional tool for exploring math visually, and certainly trigonometry is a very visual math topic. Also unique to my approach is there is a online version of this lesson at my mathcoach.me site where you can interact with these calculators directly. You can take control, you can set the angles, you can look at the various angles within the circle and why the graphed point on the cosine function is negative or positive in the various quadrants. So you can ask and answer your own questions. That's just a very effective way to learn. So let's get started. Let's take a look at graphing the cosine function and its reciprocal secant function. The description for this video does include a link to the online lesson, or you can go to the mathcoach.me site and then go to lessons and then locate this lesson here, Trigonometry 6, graph the cosine and secant function. Okay, the cosine function is also a sinusoidal wave function, and it looks a lot like the sine function. In fact, the sine function, where it starts at 0 and every 90 degrees it either peaks or hits 0 again or hits its lowest point at -1. Everything is just shifted over by 90 degrees. Okay, so very similar functions. So similar applications as well. So for modeling anything with oscillatory motion or anything with natural phenomena that has some sort of a repeating wave pattern in it as well. Okay, let's go on and look at graphing the cosine function. It's important to master graphing the cosine function. And we're going to cover all of the functions, all 6 of the trig functions. But graphing the cosine and sine function are the most important because most of your modeling tests, most of your modeling questions that you're going to face on tests, most of your transformation questions, your trig transformation questions are all going to be based on those 2 functions, the cosine function and the sine functions. Those will be the base functions for those transformation type problems. So you really want to nail those 2 down. So just like we did for the sine function, for your first graphing attempts, you can create a table like this with key angles, and I have angles at 30 degrees apart, 30, 60, 90, 120, 150, 180, and so on. So I've put them in my table for theta values, and then the cosine values, for those 30 and 60 degrees, I can just read them right off of my special triangle, my 30, 60, 90 triangle. For cosine, it is adjacent over hypotenuse, so the cosine of 30 degrees would be root 3 over 2. The cosine of 60 degrees would be 1 over 2. So you can fill out those various points, or again, look them up on a calculator or punch them into a calculator and fill out that table. Then you're ready to begin plotting. So at the cosine at 0 degrees, the cosine of 0 degrees is 1, and you can plot that here, okay? Just as a reminder, your sine function was at 0 degrees, okay? And then every 90 degrees for your sine function, it either peaked or went back to 0 or hit its minimum point or back to 0 again. Cosine function, same wave. Okay, it's just the sine function shifted by 90 degrees. But at 0 degrees, it peaks at 1. So you can plot this point, and then you can plot at every 90 degrees one of those major points. Okay, so starting at 0 degrees, we plot a point for 1. Cosine of 0 degrees is 1. Cosine of 90 degrees is 0. Okay, then we get to its most negative point, or its lowest point, of -1 at 180 degrees. At 270 degrees, back to 0. And to complete the entire 2 pi period, or 360-degree period, it returns to +1 at 360 degrees. And then you can fill in some of those other points. I like to fill in the 60-degree point, okay, and its various um, uh, values in the various quadrants. So at pi over 3, 60 degrees, and 2 pi over 3, 120 degrees. You know, the cosine ratio for those is 1/2, or could be -1/2, depending on the quadrant. Okay, so it's a good thing to plot because it really gives you the shape of the function, right? So you can plot it, particularly the way I've got this graph here. I'm putting each unit on the y-axis, or the cosine theta axis, as 1/2. Okay, so we're 2 units up, we're at 1. But we have this nice 1/2 here. So being able to plot the cosine of 60 degrees at 1/2 really gives you a good shape of your function, between, here at 1/2 and here at -1/2 at 120 degrees. It looks pretty straight, but there's always a continuous curve through this, right? Okay, just to review the properties. Properties are the same as the sine function, identical. Okay, so this could be titled properties of the sine function. So the domain is all real numbers. Okay, for your theta values, all real numbers. The range is between -1 and +1 inclusive. The period is 2 pi, and this one peaks at 0 degrees and at 360 degrees, so that's why we've marked the period at the 2 peak points. And the amplitude is absolute, the absolute amplitude is 1. Okay, so basically the distance from the center line for the function. Again, we'll use the unit circle to understand the graph of the cosine function. And as a reminder, on the unit circle, which I have here, the radius is 1, and the cosine of an angle, cosine of theta, is adjacent over hypotenuse. And on the unit circle, the adjacent side, so for this angle here, and right now it's set to 60 degrees, the cosine of 60 degrees is adjacent. Well, the adjacent side here is my x-axis. I've labeled this theta. I've labeled my y-axis cos theta, but this is your x and y, or x and y axis. So on the unit circle, when it's 60 degrees, the cosine is this value, x, divided by the hypotenuse. Hypotenuse is 1, and that's why x is equal to cos theta. Similarly, we can do a calculation where the y value, or the sine of an angle, is equal to y, the y component, or y value, over the hypotenuse, which is 1. So y is equal to sine of theta. And that's why we can use this point here to basically label the coordinates of that intersecting triangle on the unit circle. So cos theta for the x component and sine theta for the y component. Okay, let's explore this in a little bit more detail in full screen. So in this Desmos calculator, I have my cos function, cos of theta. Okay, f of theta equals cos of theta. That's this one in orange. And I also have it labeled here, and I'm using this to label it. Okay, so for every theta value, and this is in increments of pi over 6, or 30 degrees, so 30, 60, 90, and so on. For every angle of theta, I'm showing the value of f of theta, basically the plotted point of the cosine function as well. So I can move the angle within my unit circle using this slider. So right now I'm at 30 degrees, and here I'm at 60 degrees. Let's explore this one here. So the cosine of 60 degrees is the adjacent over the hypotenuse unit circle. Hypotenuse or radius is 1. The adjacent side I can see right here is 0.5 on the x-axis. So 0.5 over 1 is 1/2. And I can see that there. Cos of theta 1 is 1/2. Now, and I can also see here on my x-axis, on my theta axis, at 60 degrees, the value that is plotted is 0.5 on my cosine function. So if I move this up to 90 degrees, well, at 90 degrees, the cosine of theta is 0. We'll explore that in a moment, right? But let me go to the next 60-degree angle, or 120 degrees. So at 120 degrees on the unit circle, the reference angle, which is shown in this triangle that's inlaid in my circle, the reference angle is the angle that is adjacent to the x-axis. It has a base on the x-axis. So 180 degrees halfway around my circle. I've got 120 degrees for theta, okay? 120, my reference angle is 60 degrees. Well, we know that the cos of 60 degrees is 1/2. However, this is showing negative 1/2 because cosine of an angle is the adjacent side over the hypotenuse. Well, the adjacent side is here on my theta axis, my x-axis. Okay, and it is negative. This is my negative x-axis. So it is negative 0.5 divided by 1, and that's why it's minus 1/2. So let me jump ahead to quadrant. Well, let me just go through quadrant 2. Every angle in quadrant 2 is on the negative axis. The adjacent side is on the negative x-axis. So throughout quadrant 2, from here, from pi over 2, 90 degrees, to 180 degrees, my cosine function remains negative. At 180 degrees, it's at its maximum negative value, negative 1. Going into quadrant 3, it remains negative, okay? Let me get to my next 60-degree angle, which is 240 degrees. So 240 degrees, the shaded area on the unit circle, has a reference angle in quadrant 3 of 60 degrees, okay? So 180 plus 60 is 240. So reference angle of 60 degrees, cosine of 60 degrees is 1/2. However, on the negative x-axis, the adjacent side is negative 1/2 over 1, and that's why it remains negative 1/2. And I can see that here. So at 240 degrees, our function is plotted at, once again, 1/2, but negative 1/2. Now, let me go into quadrant 4. So here in quadrant 4, at 300 degrees, again I have a reference angle of 60 degrees. 360 minus 300, 60 degrees. Cosine of 60 degrees, 1/2. However, I've now returned to the positive x-axis. Okay, so it is 1/2 over 1, which is positive 1/2. And our cosine function remains positive throughout this quadrant 4. Okay, so as I continue to go up, notice going from 60 degrees, I have a cosine, or sorry, an x value. The adjacent value here is 1/2. It increases at 330 degrees, right? So it's increased in size, and this is beginning to approach its maximum of 1 again. And when we get to 360 degrees, in fact, the cosine function at 360 degrees is again at its maximum value of 1, completing its 2 pi period. Okay, I'm going to just let this run in animation mode. And actually, let me set it to 0 and run it this way. Okay, so as our angles are increasing through quadrant 1, I'll just pause that for a moment. our cosine function always returns a positive. Our cosine function remains positive. As it's approaching 90 degrees, the x value of this triangle, the adjacent side, is getting smaller and smaller and smaller, and it'll approach 0. At 90 degrees, it will be 0. So as it approaches, it gets smaller and smaller and smaller. Eventually, I don't know if I'll get it exactly, but eventually it'll be right at 0. I'm not going to get it exactly, but we'll continue. Now my cosine function in quadrant 2 for the angles in quadrant 2 is negative, and it'll remain negative. At 100 or at 180 degrees, it's at its maximum negative value, -1. Quadrant 3, all the angles are negative. They're getting smaller and smaller and smaller as it approaches 270, where it's 0. And in quadrant 4, back to positive values, and it'll remain positive throughout quadrant 4. And it approaches again its maximum value of 1. It hits that at 2 pi. Okay, let's continue. The secant function is the reciprocal to the cosine function. So where the cosine function is the adjacent over the hypotenuse, so cosine of 60 degrees is the adjacent side 1 over the hypotenuse, 1/2, 1 over 2. For secant, the secant is the reciprocal of that, so it is hypotenuse over adjacent. So the secant of 60 degrees would be the hypotenuse 2 over adjacent, and we get 2 over 1, or simply 2. And we can see that here in the table. In this table of values, for this table of values for theta from 0 degrees, 0 degrees, 30, 60, 90, 120, 150, all the way through to 360 degrees. I'm always showing you radians, but reading them in degrees, it's just kind of a learning process, right? You want to do that. You want to be able to convert and think in radians. Another lesson on that we've already had, but a good skill to have. So we've got all of our angles from 0 to 360 degrees, and we've got the corresponding secant ratios. So at 0 degrees, the secant ratio is 1. At 60 degrees, as we saw here, secant of 60 degrees is hypotenuse over adjacent. At 60 degrees, it is 2. Okay, so whatever the cosine ratio is, the reciprocal value. Okay, and then we see these again undefined points. Okay, let me scroll down a little bit. So wherever wherever the cosine function is 0, and it's first at 0, between 0 and 2 pi, one complete period for the cosine function, also one complete period for the secant function. Okay, so going from 0 to 2 pi, the first time it hits 0 is at pi over 2, at 90 degrees. So cosine function is 0 at 90 degrees. Well, the reciprocal of 0, 1 divided by 0, is undefined. Okay, and we have a asymptote at 90 degrees. And we have one at 270 degrees. Basically, at every odd integer value of pi over 2, okay? Of a multiple of pi over 2. So negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on. Okay, so that's where our asymptotes are. That's where the secant function will approach that line, that asymptote, but never quite get there, just as it speeds off, in this direction in positive infinity, or in this direction where the cosine function is negative and the secant function is negative, where it speeds off into negative infinity as it approaches any of these asymptotes. Okay, so just one more point on this. You might use this table one time, right, to plot this, but basically the right way to plot your cosecant function and to draw it, on graph paper is to first draw the cosine function. So get good at the cosine function, right? Everything is based on the cosine and sine function. So Draw your cosine function so you know that it starts out at its maximum value at 0 degrees, at 1, and then every 90 degrees it hits one of those major points. At 90 degrees it goes to 0. At another 90 degrees, at 180 degrees, it's at its most negative point, -1. At 270, it's back to 0. And at 2 pi, it completes its cycle. Again, it's at its maximum value of 1. Once you've drawn your cosine function, then at all of the cosine function's extreme values, most positive or most negative values, it intersects with the secant function. So where the cosine function is 1 here and here, we have an intersecting of the secant function. So you can plot a point there. Also, where it's negative, so where our cosine function at 180 degrees is at -1, you can plot a point for your secant function at -1. So they intersect there as well. Draw in all of your asymptotes. So wherever your cosine function goes to 0, you can sketch in an asymptote, okay? Just a light line indicating that your secant function is going to approach that line, but it's never going to quite get there, okay? And it's undefined right at that point, okay? So it never crosses that line. And it continues on this side, right? So you draw in your asymptotes. It's useful to plot the 60-degree points as well. So cosine of 60 is 1/2. The secant of 60 is the reciprocal of that, 2. So plotting, that point there helps to give you the shape of each arm of the curve, okay? And that's basically how you plot it. Now we're just going to sum up with the properties. So the properties of the secant, it is all real values for theta with a couple of exceptions, okay? It is undefined at the asymptote. So at, all real numbers except odd integer multiples of pi over 2. And that's where the asymptotes are as well, the vertical asymptotes at odd integer multiples of pi over 2. The range is from +1 to infinity, wherever the secant function is positive, wherever the cosine function is positive, and it is from -1 to -infinity, wherever the secant function is negative or the cosine function is negative. This Desmos calculator is showing us the relationship between the secant function and the secant ratio and the cosine ratio, its reciprocal. And it's also showing us a unit circle as well. I have a unit circle where I can control the size of the theta angle. So I've got in purple our secant function and in orange our cosine function. And I also have these plotted points here for the cosine function and the secant function. So for different sizes of theta, I'm also showing where that point will plot on either of those two functions. So starting out with, well, let's move this back to 0. Okay, so when theta is 0 degrees, my cosine function is 1, and we know how to plot that. Well, so is my secant function. Okay, so they intersect at all of those extreme points, okay, on the cosine function at the +1 points and the -1 points. So we can see that there's an intersection there. Both functions, cosine and secant, are equal to 1 at 0 degrees. When I increase this, and I'll just slide it this way, so at 30 degrees, I can see the value of my cosine function is √3/2, and the secant function is the inverse of that, 2/√3. And if I slide that up to 60 degrees, so at 60 degrees, my cosine function is 1/2, 1/2, and I can see that here. The secant function is the reciprocal of that, and I can also see that here. Cosine function 1/2 for 60 degrees, secant of 60 degrees is equal to 2. So moving on to my next 30-degree increment, pi over 2, cosine function of 90 degrees is 0. The reciprocal of that is undefined. 1 divided by 0 is undefined, and I no longer see a dotted line like I saw at these other angles that is showing the relationship of those reciprocal values for those two functions. So at 90 degrees, undefined for the cosecant. So basically, our cosecant function, as it's approaching 90 degrees, it's getting larger and larger and larger. It's approaching positive infinity, never quite get there. On the other side, so as we leave quadrant 1 and go into quadrant 2, and we're going in 30-degree increments, so at 120 degrees, this is another version of our 60-degree angle. At 120 degrees, our reference angle is 30 degrees, and our cosine of that angle, our cosine of 120 degrees is negative 1/2. The reciprocal of that, the secant, is at -2, and we see that here and here. Cosine function will be negative throughout quadrant 2 and quadrant 3, and so will the secant function. They are both negative within those two quadrants. As we continue, we get to 180 degrees where again they intersect. So at 180 degrees, the cosine of 180 degrees is -1. The secant of that is also -1. Continuing on through quadrant 3, we can see that in our unit circle. We remain negative. Our cosine functions and values are getting smaller and smaller and smaller. Our secant functions are going to get larger and larger and larger, approaching negative infinity until they get to 3 pi over 2, 270 degrees, where our cosine function is 0. We have an asymptote that basically indicates that the secant function just is not available there. And I'm using this little formula here. Basically, at every odd integer multiple of pi over 2, there's an asymptote. That's where the cosine function is 0, and the secant function has an asymptote. It approaches that, but never gets there. Okay, continuing through quadrant 4, okay, now we're into the positive zone, where we have positive x values for the adjacent side. So our cosine function is positive, our secant function is positive, and we get to the complete end of that period or the end of that cycle once around the circle at 360 degrees. Both of them are back to 1. Now, just want to explore a little bit more on what's happening as it's approaching that pi over 2 value, okay? So I'm just going to actually put in pi over 2. Okay, so at pi over 2, at 90 degrees, the cosine of 90 degrees is 0. Secant is undefined. Now, what I'm going to do is I'm going to subtract from that 0.1. Okay, so at pi over 2 minus, this is 1.57 something, minus 0.1, we can see that my cosine function is, it's pretty small. It's about 0.09, it's 0.1, right? And my secant function, the reciprocal of that, it's around 10. Well, I'm going to just pad this with some zeros. So I'm going to add even a smaller number to pi over 2, or subtract a smaller number from pi over 2. So I'm getting pretty close to pi over 2. Pi over 2 minus 0.01. My cosine function has gotten even smaller. My secant function is now up to 100. And I'm going to just add, well, another one. My secant function is now up to 1,000. So as that number gets smaller and smaller, and I'm getting closer and closer to pi over 2, my secant function begins to approach infinity. My cosine function begins to approach 0. That's a real small number, 9.9 times 10 to the -7. This is a million. Okay, so we're starting to approach infinity. Not there yet, but, let's just throw in some zeros. Okay, so, all right, what does this number read? 9.9 times 10 to the minus 11. That's a gazillion, billion, whatever it is. It's a huge number, okay? So as we get closer and closer to those asymptotes, wherever they are, right? In this case, as we're getting closer and closer to 90 degrees, our secant function, our cosine function, is approaching zero, its ratio. Our secant ratio is approaching positive infinity. Now, when we get right at pi over 2, cosine function is 0, secant function is undefined. What happens on the other side? If I were to change this negative sign to a positive sign, I am now on the other side of pi over 2, and I'm into the second quadrant. You can't see it here, but we are, okay? So the cosine function of pi over 2 plus 0.000001 is a pretty small number, okay? -1, it's negative. It's gone into the negative territory. -1 times 10 to the -12. And our secant is quite a large number, 9.9, -9.9 times 10 to the 11, right? And now I can kind of like move away from that. So as I begin to get further and further away, watch that secant function. It's starting to get, smaller and smaller. I mean, it's still a pretty big number, but it is getting smaller. So as I'm starting to get further and further away, we really haven't seen it move yet, right? But that secant number, now it's a number that I can actually read, minus 10,000, okay? And, now it's minus 1,000, right? Now we're actually starting to see it move again. Now it's minus 100, right? At pi over 2 plus 0.1, now it's minus 10, okay? So that switch over as we cross that pi over 2 line. At pi over 2, we have an asymptote for the secant function. It is undefined. On the less than pi over 2 side, as we were approaching it, it was going off into positive infinity. As soon as we cross that line, it started coming back from negative infinity. So just wanted to explore that. I'm going to just let this run. And that's not running. Oh, let me just remove that. Let's just let that run. Okay, so through the animation, you can just basically see kind of and watch that relationship between the cosine function and its reciprocal secant functions. And you can see what's happening at the asymptotes. It was at positive infinity. Now it's coming back from negative infinity. And they're both approaching -1. And at 100 or 180 degrees, they'll both be at -1. And now as they approach 270 degrees, my secant function is going to approach negative infinity, and just on the other side, it's coming back from positive infinity, okay? Okay, that concludes this lesson on graphing the cosine and secant function. If you like my approach and you're gaining a better understanding of trigonometry, be sure to like this video and follow my Math Coach Me channel. Also, check out the interactive version of this lesson. You can find a link in the video description. And finally, in our next lesson, this graphic's from our next video where we're going to take a look at graphing the tan and cotan functions. So we'll see you then.